is Stephen Kell from King's College London. I'm your session chair. And we have two talks today. We have a shorter talk, which is a paper talk, and we have a longer talk, which is an essay talk. And our first speaker is Max, who's going to tell us about X-by construction towards ensuring non-functional properties in by-construction engineering. Take it away, Max.
Thank you, Stephen. Next one, please. Welcome to my talk on X-by construction and how we envision integrating non-functional properties of software quality into by-construction engineering. Very complicated title, and before we get to what by-construction engineering is, I want to thank my co-authors, Tabea, Alex, and Ina, for contributing to this paper. We're going to have a look at a major concern that every developer, every software developer, probably all of you, somehow face when you develop a program, and that is software quality. And if I would ask you what you connect with the term software quality, I would assume that this is correctness. Your program should do what it is intended to do, but depending on the domain you are working in or you are developing your program for, there can be different focuses. All of them have in common that software quality is important. Otherwise, your program will fail. There will be costs, consequences, maybe even endangering human lives. But software quality is not only about functional correctness, but also other properties. This is from the ISO 25010 standard. They define software quality or software product quality in 9 different properties. On the left, you can see functional suitability. That is a bit weird. I will call it functional correctness in this talk. But this means exactly the same. And we have 8 different non-functional properties that are split into sub-properties that describe the main property. Usually, correctness is still important, and the main driver, as a program that is not doing what it is intended to do, but is maybe very safe, is still of no use. So your focus is usually on functional correctness. And functional correctness is commonly ensured by testing. That is probably what all of you would do when you start developing something. But as we heard, I think yesterday in some talk, also Dijkstra said that you can show the presence of bugs, but not their absence, as you can't test all inputs. An approach to actually guarantee that a program is working as intended is formal verification. And for those of you that attended, I think it was the first keynote on Thursday, that might know a bit about formal verification. And for those of you that didn't attend or don't remember, just a small recap, what is that? Formal verification is an approach to guarantee that a program is working for all possible inputs and is based on logics and mathematics. We prove our program according to a formal specification and check whether the program fulfills this specification. Common approaches are model checking and deductive verification. And those two and also other approaches have in common that they are applied after you actually implemented your program. So you have 2 parts, your implementation and your specification, and then you have some nice tool, hopefully, or you do it by hand, and prove that those 2 fit together, and your program actually fulfills the specification. The approaches where you have both before starting verifying are called post-hoc approaches, so they are only applied after you are done with your implementation. An alternative are so-called, or is, correctness by construction, in short CBC. This offers advantages because you can start verifying earlier, so you don't have to complete your whole program to start receiving information on whether what you did is correct or not. CBC is a refinement-based incremental approach and is based on the formal specification. So for post-hoc approaches, it would be possible to write your program and your specification 3 weeks later. This is not possible for CBC. You have to write your specification first, because based on the specification, you apply different refinement rules. Refinement rules represent basic programming constructs like selections, loops, assignments, method calls, and so on, and are applied on an abstract program that you want to concretize to an actual concrete program. And the nice thing about CBC is that you can verify each of the refinement steps. So each refinement rule comes with so-called side conditions that you can check. And if this check, or the verification, is successful, you know, okay, this application was valid and still fulfills the given specification. And in the end, the result is the same as in post-hoc approaches. that's the correct implementation, in this case even correct by construction. As a summary, advantages, we still have proven correct programs as in post-hoc verification, but we get earlier feedback on the correctness of our program. And also, if a proof fails, we already know at what point in the program we have to look for a bug. In post-hoc verification, you just know, okay, at some point in the program, there's a problem. But as we have a very fine-grained verification, we can already localize the bug very easily. So how is that looking in practice? Okay, forget the second point, that shouldn't be there. We start with a Hall triple PSQ, where P and Q are our pre and post conditions, the specification, describing the intended behavior. And in this example, we want to implement a searching algorithm. So we have a precondition that just says, okay, we have some array A that should be initialized and contain at least one element. And we have a post condition Q that says if there is our element X that we're looking for in this array A, then we want to have some pointer or pointer I in the end that points to this element we are looking for. And now we can start applying refinement rules. For the first one, we would apply the composition refinement rule that just splits our abstract statement S that we want to implement into two, because otherwise we could just like apply one assignment or one loop, but nothing else. So for now, we would apply the composition rule, which comes with a side condition, which sounds like we need to be able to define an intermediate condition, in this case M, that is valid after executing the first statement S1 and before executing the second statement S2. So basically, we split our single abstract statement S into two. And then we can continue with, for example, initializing I to the last element of our array and creating a loop with a loop body that iterates from the last element to the first in our array until we found X. And in this tree, we can verify each of the nodes individually and in the end have a correct program. So back to software quality, we can ensure functional correctness using CBC, and there are approaches for all the other properties as well. I'm pretty sure for all of them, maybe almost all of them. What they have in common, as for post-hoc verification, usually they are applied post-hoc. So you have to implement your program first before you can start ensuring, proving, whatever, your non-functional property. And the question is, or the problem is, that you only get that late feedback. Your program might even be deployed because you have like a deadline, and you figure out, okay, my software for some plane or healthcare is already deployed, but I didn't ensure other properties. And we asked ourselves, okay, why not combining the advantages of CBC with the early feedback also with non-functional properties? And previous colleagues of mine started doing that for security. And there are two techniques that are a result of that work. That is confidentiality, C14BC by construction, and information flow control by construction. Both of them fit to the security property in the table you just saw and ensure information flow policies. So we can, for example, ensure that a high security variable is not leaking information to a low security variable through both direct and indirect information flow. However, those two are the only ones and are referred to as X by construction. So the summary of techniques for non-functional properties in by construction engineering is XPC. The X in this case is a random non-functional property you could put in there. However, those two is the only work that happened so far, and that is why we thought, okay, let's have a look on the other properties that are still there and not covered yet. Resulting this gap, we thought of our vision, and that is also what our paper is mainly about, how we imagine extending XPC and by construction engineering to cover further non-functional properties, to have like a programming paradigm for high-quality software. Still, functional correctness should and needs to be the main driver of program construction. As I said earlier, a program that is not doing what it's intended to do is of no use. But we imagine flexible and customizable integration of non-functional properties in your development process, always depending on your use case. Maybe you have a program where you say, okay, that needs to be fast, but I don't care about security. I don't know if that's clever, but anyway, you should be able to set that focus. Also, we want to maintain as abstract as possible. So we don't want to have, or we want to have as few as possible dependencies to the remaining structure of our system and also the hardware that our program might run on later on. And finally, also to maintain usability, we imagine some kind of tool support for CBC and also the existing techniques of IFBC and C14BC. There is tool support, which should be extended and made be usable. The result, as I just said, should be a paradigm to be able to create high-quality software, not only for ensuring functional correctness, but also non-functional properties. And we said ourselves, okay, we have a vision now. Where should we start? There's like a wide range of properties that one could cover, as you've seen before. And we decided to look at them and see which of those are likely to be integrated into XPC and which are maybe a bit more difficult. And based on the existing work, we defined 6 requirements where we think that they need to be fulfilled to be actually able to integrate a property into XPC. The first, and that is the starting point also for CBC, is somehow a specification. We need to be able to define how this property that we want to integrate should look like in the end. For functional correctness, it's just the specification, the functional specification. For IFBC, for example, we can declare what variables have what security type, and this needs also to be possible for other properties. Yes, as I said the slide before, in our vision, we want to be as abstract as possible for 2 reasons. We don't know the structure of our program because, we just didn't start implementing it yet. And also, we want independence between other properties. So you could say, okay, maybe a program is really quick but consumes a lot of energy or is not safe anymore. So there will be interferences between certain properties, and we want to maintain either independence of them. That won't be possible in all cases, but for the cases where it is not possible, we want to have some rules how to handle them. The 4th requirement is that we somehow need to be that we need to be able to check if our property and the specification that we defined earlier is fulfilled or not. The 5th requirement, and that is one that is applicable on multiple levels, is compositionality and modularity. We have 2 points. We have like the program itself that you saw earlier and the program in the CBC tree, where we can say, okay, we only have a part, but we need to be able to reason from the part of a program to the whole program, and we have compositionality on the whole system level. So if you imagine energy consumption, we'll have a look at that later, there are dependencies outside the program we're just constructing. There's a whole system, there's hardware. And finally, the last requirement is the combination with the refinement rules that are existent in CBC, which are the main driver, which need to be able to somehow fit, or the new functional non-functional property needs to be able to fit into those rules so that the non-functional property can be assured on the side while using the refinement rules of CBC. And we assessed the properties that you saw earlier on the table, whether those requirements are fulfilled or not. And you'll see a table with the properties on the left, the requirements on the right, and whether they are fulfilled or not. We did a bit of literature research, and you will see that there are like check marks and also check marks in brackets. The ones in brackets are, let's say, partially fulfilled, or certain of those sub-properties you saw earlier are fulfilled, but not all of them. Those 2 are already existent in CBC and IFBC for correctness and security, and you can see, as we all expected, that the requirements are fulfilled here. For performance efficiency, so that is time, memory, energy, and so on, we can also fulfill the requirements, some of them under certain conditions, and the same for reliability. For safety, compatibility, and maintainability, it's a bit worse. So those three are currently not planned to be integrated into XPC. And for those of you that have a very good memory, yes, there were two more on the table. That is flexibility and interaction capability. We didn't assess these because they are too far from the actual code level that we are looking in CBC, but more on, let's say, management level. So we didn't assess them in this paper. Based on the results, we decided to have a look at performance efficiency first. And as we are in a world where there's climate change and sustainability, we decided to look at energy first. The ISO 25010 in this term says energy efficiency. For us, we look at energy consumption, so the actual energy that our program might consume when running. And now we might think, okay, we are on a program level, and I just said we have dependencies, and to both the system, the remaining system, and also the hardware we might run our system on in the end. That is why we said, okay, we have ideas, but this is not like a final concept, just a starting step towards integrating energy efficiency into XPC. And there is like a kind of gap. As you might imagine, we have like high-level code in CBC. So our tool produces Java code, and depending on your compiler, your hardware, there will be different energy consumption. So you can't just like map the Java code to a certain energy consumption. That's why this is all just like a sketch. There will be some hardware model later, but don't take that too serious for now. The first step, as I said earlier, we need to have some sort of specification for energy. And we want to stay abstract, so it's kind of hard to actually say, okay, how would that specification look like? We had different ideas of having concrete values. Our program should maybe, as an upper bound, consume 5 joules. We could say, okay, we have intervals, like 3 to 5 joules. Or we could go for an approach like in information flow control by construction, where we have different levels of high, medium, low energy consumption. For now, we decided for abstract, uninterpreted symbols that somehow, it says count, I don't like the word, but still count the energy that is consumed in our program. And those symbols, there are 4 of them, for writing, reading, binary operations, and returning variables. Those 4, we chose them because they fit our use case. There's no other reason for that. And we want to step through how this process would look like. And this is the same that you saw earlier for linear search, so it looks a bit different, but in the end it's almost the same. So the hot triple PSQ extended by some energy annotations. So in our precondition, we say, okay, we don't want to have any energy consumed yet. You could say, okay, there will be energy consumed in some prior program state, but we don't look at that now. And for the postcondition, as I said, it's hard to specify what energy will be consumed because we don't know how our program will look like. That's why, for now, we're more like in a tracking mode instead of actually specifying it beforehand. So for now, we say our postcondition or our energy annotation in the postcondition is undefined because we don't know of the structure yet. And now we can start doing the same that we did earlier, apply refinement rules. In this case, we would again have that intermediate condition that needs to be fulfilled after S1 and before S2. And we have the same here in blue. Our intermediate energy annotation is undefined for now. But as soon as we have the assignment on the left, where we initialize our iterator variable, this undefined becomes concrete. So for the operation or the assignment of the subtraction of the length of array A minus 1 to variable k, we can say we have 1 reading, 1 writing, and 1 binary operation, or the energy that those operations consume. And the same is happening on the right side for the loop. Don't be confused. That method or that implementation is extended by a return value. That's why the tree is slightly bigger than the one that you saw earlier. And the more we implement, the more of the undefined energy annotations become actually concrete. And you can see now in the end, when the program is constructed, our post condition is also not undefined anymore, but we have the concrete energy consumption of the whole program. And now the question is, what can we do with that stuff? One could say, okay, yeah, that was possible before. We don't need CBC to actually get that term up there. But the nice thing is that with those fine-grained energy annotations, we can work with families of algorithms. Think of sorting or searching algorithms. You have a lot of implementations. They all produce the same result, but have a different structure. And one could start now, okay, implement different, for example, searching algorithms with CBC and compare parts of them. There are similarities, and one could figure out, okay, algorithm A takes less energy in this part of the algorithm than for algorithm B, and maybe improve one of them. Yeah. Another direct application would be to put in values. As I said, there's somehow a gap between our high-level Java code and the actual hardware we would run on. However, we jumped over that gap and mapped our energy annotations, the 4 on the left, to concrete values for hardware for PTX, or hardware model for PTX instruction level with concrete values, in this case a nanojoule. And now we could say, okay, we take the energy consumption or the energy annotations of linear search and also for second implementation of binary search and initialize them with the values of our energy model. This would look like this. You would expect for linear search, we have some linear energy consumption, and for binary search, it's logarithmic as we split the array always in half. And now, we can put that in a diagram. That is what you would expect. Blue is linear search and green is binary search. And if we look at it closer, we can say that for array length between 0 and I think that is about 12, linear search consumes less energy than binary search, and from that point on, binary search would be more efficient. I already mentioned some of our challenges and especially limitations of the approach you just saw. So we have that limited expressiveness because of this gap. We saw that just in the keynote this morning. So different abstraction layers might be some approach here. Also, the dependencies to system and hardware that I mentioned earlier. For all non-functional properties, not only energy efficiency, but also the remaining ones, we have the modularity and compositionality issues, as most of them can't be looked at completely local. And finally, we still want to be able to apply this in practice. So what you just saw with the energy annotations, that could be automated kind of quickly, but the tool support for that is not there yet. And when you think about having more non-functional properties and having these interferences that I mentioned in, I think it was the third requirement, we somehow need to be able to make that usable. Yeah. So what are we doing now? Currently, we are refining the idea of energy annotations and formalize them. Like, this is a formal methods topic, so somehow we need to prove that what we are doing is actually true. This concept is called energy efficiency by construction, and maybe you'll read something about that next year. We are looking at closing this gap between low-level energy models and our high-level programming language by looking at Pancake, language mainly used for developing drivers, so hardware closer. We're also looking at reliability. That is because reliability also fulfilled the requirements that we saw earlier. Now you could say, okay, we have a program that is already proven correct. How should that not be reliable? We are abstracting from the program level to a component level. So imagine you have components that are constructed using CBC or some other formal verification technique, but there might be components that you didn't verify, that are maybe just tested or even learned components. How would that look like? And finally, the other performance efficiency properties, memory time, and so on. Yes, and again, to support. And with that, maybe the most detailed look on software quality you ever did. I showed you CBC and hope you got an idea on why this is a nice idea, and also presented our vision. And we had a look at first ideas for energy annotations. And with that, I'm done. Thank you for your attention, and I'm really open to answer questions.
Please go to the mic. Thank you.
Hi. Thank you for the cool talk. I'm really wondering, so with the, thank you. So for this energy efficiency by construction thing, I'm curious to see how you've sort of separated it from like some sort of hardware and architectural concerns, even though you instantiate with like the energy constants for PTX instructions at the end. But I feel like my understanding of a lot of this efficiency and energy consumption also relies on things like size, structure of cache lines, and also as we're talking about like the most energy consuming programs running right now are machine learning workloads. Those are running on like vector machines, GPUs, and like some of these more like specific machinery. So do these constants still hold meaning, or is this like extensible to accommodate these kinds of architectures?
No, that is a very abstract and basic idea. So we didn't take those into account, but that is what is happening in the current work. So that we somehow take those dependencies into consideration. I mean, the mapping of the PTX instructions and our energy annotations, that is very easy and too easy. That's not how it's happening in reality. So yeah, that is part of ongoing and also future work.
Cool, thank you.
Hey, thanks for the talk. So I was wondering, like, could you say that the energy annotations are like a more precise way to determine the complexity of an algorithm, right? Because normally we discard the constants and the smaller, factors.
Yeah, I mean, the complexity was kind of the result that you saw when we did the instantiation with linear and logarithmic consumption, and that is also what you would expect in complexity theory. The fine-grained part is kind of the core of by-construction engineering, that we don't look at the whole program, not only in functional correctness and not only in the energy annotations, but in all properties.
Right. So the complexity would be like a lower bound, probably, right, on the energy? Something like that. Okay, thanks.
Also wondering, you had this table of all the different quality metrics you could be interested in, and then it was kind of a sad ending that most of them we can't do in this correct by construction thing.
Yeah.
I think maybe if we move outside of this sort of four triple kind of strategy for correct by construction, there may be some ways to get some of the CBC benefits for the other rows, or how do you think about that? Is it just a lost cause?
Yeah, so that is kind of addresses the point of reliability that I mentioned on the future work slide. At some points we are not on program level anymore. Yeah, so we need to go on a different level, either component level, maybe for certain properties even on system level. But that is something that we didn't focus on in this paper, but that might definitely be something to look at.
Thanks. Okay, we seem to be out of questions, and I think we're bang on time. So let's thank Max again for a very interesting talk. Okay, how are you doing, Kartik? Are you feeling ready?
I'm getting there.
Okay, I'll give you a moment.
Yeah, well, okay. I guess the mic is working because
Yes.
I hear myself. Great. Let me continue to connect wires to other wires.
I'm very intrigued by the title of this essay, let me say. So,
Well, Okay, so I think those are my slides. That's a good sign.
Yay.
And sorry, the last thing I need to do is open this deck of cards.
It's even more exciting.
I'm ready.
Great. So this is our last talk of the session and of this year's Onward. It's about an essay that is already intriguing me, and our speaker is Kartik Chandra. And take it away, Kartik.
Thanks, Stephen. I think it's the case that from time to time, we all have crises of identity. We have these moments of radical and overwhelming doubts about the nature of ourselves. I don't really know if these doubts can be externalized in words and natural language, but if I were to try, I would externalize them as questions. Questions like, who am I? What am I? What kind of person? What kind of mind? Whatever the question is, it creeps up on you. Perhaps it's crept up on you when you were deciding where to do your PhD, or deciding whom to marry, or deciding whether to forgive someone, or perhaps it was rattling around in your head when you were faced with a failure or a regret or some kind of overwhelming personal loss. This talk is about programming languages, and I promise that in about 15 minutes, these slides are going to be covered in scheme code, and perhaps that will make you all happy. But this talk is secretly also about a time that the question crept up on me. It was the spring. I was 25, and I was at a friend's apartment sitting on her couch in the sort of melancholy and heartbroken way that one can only really be in one's mid-20s, I think. And I sat there with my friend and was talking, and suddenly I felt it. There it was, the question, who am I? What am I? What kind of person? What kind of mind? And we sat there, the two of us, and we talked about these questions. And then, kind of oddly and kind of suddenly, I had this sense of deja vu. I felt like I had seen these questions before. I'd thought about them before. I'd felt like this at some point in the past. And kind of abruptly, and perhaps even a little rudely, I got up from my friend's couch, and I got on a bicycle and rode home back to my apartment. And I rushed in, and I ran to a cabinet, and I opened that cabinet, and I pulled out a stack of notebooks, a stack of journals, actually, that I'd kept for many years, ever since I was a little kid. That's a picture of me as a little kid. And I thought, okay, surely if there was a time in the past when this question had snuck up on me, then I would have thought about it and I would have written down what I thought. And perhaps if I were to read the prior work, I would have a bit of a leg up. I would have a head start on figuring out where to go from here. I thought, in short, that what these journals contained were candidate answers. Call them theories of self posited by my own mind. So I settled into my own couch in my own apartment, and I started reading these notebooks. It was maybe 9 or 10 at night. And, well, I think you can actually guess what happened, right? What happened was I started reading and immediately had this flush of embarrassment. And I looked at the writing of my 15-year-old self, and I thought, these theories are all bunk. Right? No one knows anything about themselves when they're 15. Certainly I didn't know anything about myself when I was 15, and the writing, it made me cringe, it made me feel embarrassed. And I thought, not only am I embarrassed at the object level of the writing in these notebooks, I'm embarrassed at myself at the meta level for thinking that there's any way, any chance, that by looking at something I'd written when I was 15, I could learn about myself now in the present at age 25. So I sat there feeling a little bit sheepish, feeling a little silly for having found myself in this position. And then I kept reading. I don't know what it was. Call it morbid curiosity. I don't know. I kept turning the pages. It was 11 o'clock, 12. I think it got up to like 1:30 in the morning, and I kept reading these journals. And I had this odd feeling that even though I knew that these theories were bunk, I was somehow learning something about myself. And that was weird. How is it possible to learn something true about yourself by reading theories about yourself that are false? That seemed odd. That seemed disturbing. And I sat there and I thought about it for a moment, and then it hit me. What these journals contained, they contained theories of self, but also, in a sense, they contained data on the theorizer, by which I mean they contained traces left by my own mind. And if I were to look at those traces and treat them as data, like data from an experiment, then perhaps I could induce new theories, new meta-theories of my own in the present. What a strange learning mechanism this is, if you can even call it a learning mechanism. How could it be possible that it is possible to endogenously bootstrap some kind of self-knowledge from nothing? The mechanism, to be clear, is this. The mechanism is to learn something about yourself. What you do is you ask yourself, who am I? And then you make a guess. And because you're a child, you have no hope of getting it right. You make a guess and it's probably wrong. But then you look back at the guess you made and you think, well, what kind of person would guess that? And then you think, okay, well, now I know a little bit more about myself. And then you make a second guess. And this process goes on and on and on. And the theory is, perhaps by doing this you learn something. But this should give you pause. This should be philosophically disquieting to you, because how can you get something from nothing? That seems weird. It seems weird, yes, but I've come to believe that this really is a way of knowing, perhaps even the only way of knowing about ourselves. It's as the Cartesian argument goes. In the face of radical and overwhelming doubt about the self, the firmest ground we have to build on is cogito ergo sum, reflection on reflection. Though to be clear, I don't think you have to be a professional philosopher. You don't have to be an angsty grad student to think in this way. I think every human being, every child, every baby is born and faced with this extraordinary philosophical puzzle of organizing the blooming, buzzing confusion of cognitive experience into some sort of theory of self, some sort of theory of mind. And because the strongest signal about our thoughts is our thoughts, the way forward is reflecting on reflection. Now you might say, okay, Kartik, this is a nice story you're telling, that somehow we can learn something about ourselves by thinking about our own thinking. But the only problem is, surely the primary way in which we learn is not by reflecting our own thoughts, but rather by reflecting on the thoughts of others. We learn from our teachers, our friends, our parents. We learn from authors of books. And I think that's true. Surely we learn from all of these sources. But then, where do our teachers, our parents, our friends, authors of books, where do they learn from? Let's think not at the level of an individual now. Let's think at the level of a society or a culture or a community or a species. Certainly at the level of a species, there's nothing exogenous to tell us who we are. As humanity, we are born strangers to ourselves, and all we have to go on is our own reflections. This, I think, is the history of human thought. The history of human thought is people. By people, I mean painters, I mean scientists, I mean writers and philosophers, people articulating theories about what it means to be human, and then looking back at theories of the past and learning from them and saying something new about what it means to be human. I think this is this grand intergenerational baton pass that we are all a part of. Now, I want to be super clear about the kind of baton pass I'm talking about here. I'm not talking about the mechanism by which we refine theories of the world over time. So I'm not talking about the mechanism by which, let's say, Galileo articulates some theory of how bodies in the world move, and that theory is refined by Newton, which is then refined by Einstein. I think this mechanism is interesting, important, deep, and beautiful, but it's not what I'm talking about today. What I'm talking about today is the mechanism by which Galileo articulates a theory, and then someone like Thomas Kuhn looks at that theory and uses it as a case study on the theorizer, as a case study on the human mind's capacity for making theories at all, as Kuhn did in his book, The Structure of Scientific Revolutions. Or as Alison Gopnik did when she reflected on Galileo's theorizing as a case study to make an analogy to how children learn about the world in her book, The Scientist in the Crib. I'm talking about sciences here, but I think this happens everywhere. And I think, in fact, the strongest examples come to us not from science, but from art. I'm thinking of a painting whose title is Where Do We Come From? What Are We? Where Are We Going? By Paul Gauguin. And of course, the title of this painting is just another way of saying the question, who am I, what kind of person, what kind of mind? This painting hangs in the Boston Museum of Fine Arts. It's actually not very far from MIT, which is where I go to grad school. And I have spent so many hours of my graduate career sitting on the bench in front of this painting at the Museum of Fine Arts, looking, thinking, yearning, wishing that perhaps if I looked at this painting long enough, I could read off an answer to the question. Because after all, isn't this canvas really just a theory articulated by Paul Gauguin, a theory as to who we are or what we are? The only problem is I don't think that I can take this theory seriously. And the answer, and the reason for that is, well, if you're not in the know, Paul Gauguin is kind of a controversial figure. The scholarly consensus on him is that he brought with him a racist, colonialist, sexist attitude towards the subjects he painted, who were the native people of Tahiti. He saw them as savages who had to be civilized by the Europeans. And I can't take seriously a theory of what it means to be human coming from a person who saw other humans as less than human. That just doesn't click for me. And so I think that this theory must be bunk. But then again, at the same time, I look at the man who's looking at this painting and I think surely he is learning something about what it means to be human, but how is that possible? It must be possible because this painting, yes, it articulates a theory of what it means to be human, but it's also data on the theorizer. It teaches us something about our own capacity to look out at our fellow people and see not people, but something less. And that, in turn, I think, allows us to induce new theories of what it means to be human in the present. Okay, so I have articulated for you a candidate learning mechanism, a way by which human beings might learn something about themselves by reflecting on their own reflections, either in the mind of an individual in the here and now, or the mind of a species over its history. But surely by now, you are very, very uncomfortable, perhaps skeptical, perhaps about ready to get up and walk out of this talk, because of course, like, how could it possibly work this way, right? Like, this just seems circular and wrong and bizarre. In fact, let me offer you 3 reasons why this just seems completely implausible. Reason number 1 is what I call the circularity objection, which is there's no such thing as a free lunch. You can't get something from nothing. How is it possible that with no exogenous signal, a mind can just bootstrap endogenously some sort of self-knowledge? That just seems impossible. That's the first objection. The second objection is this empirical observation that our best AI systems certainly don't work this way. If you take a large language model and you train it on its own output, it does not attain enlightenment. It does not learn about itself. It actually starts decomposing and producing gibberish as output. That's an empirical objection. And then there's a representational objection, which I will just read out verbatim because I think it is phrased so poetically. This is from Emerson Pugh, who writes, "If the human brain were so simple that we could understand it, then we would be so simple that we couldn't." I accept all of these counter-arguments. I think these are valid objections. I think they're thoughtful, and I think they're forceful. But I've been around you people, I've been around PL researchers long enough to know that when in the face of reflection on reflection, when in the face of this kind of meta thinking, it pays to be a little cautious. It pays to be a little open. I have learned to be skeptical of things like a set that contains itself or a machine that simulates itself. All sorts of weird things happen there, and I've learned to be a little wary of a compiler that compiles itself. These objects defy our intuitions, and so I'm willing to be surprised in this case as well. But if I were to be surprised, I would like to do so through the wide eyes of the programming languages researcher. And so what I'd like to think about is, as a programming languages researcher, what's the minimal model of this kind of endogenous bootstrapping of self-knowledge? And I think, of course, whatever this minimal model is, it must be a program. But what kind of program? Okay, well, I think it's a program of whom we demand the question, who are you? Which is to say, what is your source code? And okay, the program then is forced to guess its own source code, but of course, in the beginning, there's no hope. Like, it doesn't know. You know, we are born strangers to ourselves. So the program makes a guess. It thinks I'm X. And X is probably wrong. But then we ask it again. We say, okay, what is your source code? And by the way, the first time I asked you, you said that you were X. And that little bit of information should allow it to learn just a little bit about its own source code. And it should make a better guess this time. It should say, well, given that I previously guessed X, I now think I'm Y. And then, of course, we can keep going. We can say, okay, again, who are you? And let me just say, the first time I asked you, with no information, you said you were X. And when I asked you who you were, and also said that given X, you guessed Y, and I also tell you that given X, you guessed Y. And based on that, the program should make a new guess, Z. And the hope would be that if we loop this over and over again, that eventually it would reach some kind of fixed point, and the fixed point would be repeatedly guessing its own source code over and over and over again. This kind of program is similar to a quine. It's similar to this type of program that prints out its own source code. But I think of a quine as like a nativist solution to the problem, right? Like if you've ever written a quine, the way you do it is by like embedding a little bit of the source code into the source code. Whereas what I'm proposing, the program that I want to write with you all, let's call it not a quine, let's call it a gogine. A gogine infers its own source code. It's an empiricist. It learns from its own experience of itself. So the goal of this talk is to write such a program. And that's what I'm going to do in the rest of this time. All right, what kind of program are we writing here? Well, we're writing a program that makes guesses under uncertainty about itself. And so it's not just a program, I think it's a probabilistic program. And so I wanted to start off by giving you a couple of etudes just to warm you up to the idea of probabilistic programs that make inferences about the world under uncertainty. All right, here's the first etude. Suppose you've got a friend, suppose arbitrarily she's named Quinn. Quinn comes to you holding two dice, a red die and a blue die. She shakes them up and she rolls them, but doesn't show you the outcomes. Quinn says, look, these dice, the sum is 7. And then she asks you, what is the probability that the first die came up 3 or more? You all know how to solve this problem, right? Here's how you do it. You write out the space of all possible outcomes. There's 36 of them, 6 times 6, and they all have the same probability, 1 in 36. Then you pick out or condition on the outcomes that you know are possible based on the information you have, and then you integrate over the desirable outcomes, and then you just read off the answer. The answer is 4 and 6. The probability that the blue die came up 3 or more is 4 out of 6, or 2/3. Let me show you how you would write a probabilistic program that does the same calculation automatically. So I'm going to use a programming language called Church. And what Church is it's just scheme, but with a couple of additional primitives. The first primitive lets you set up probability distributions. So for example, we can say that a die is just a uniform distribution over the numbers 1, 2, 3, 4, 5, 6. The second primitive is called infer, and what infer lets you do is do a bunch of probability operations inside its body. So for example, given this distribution die, we can sample from it. We can say that the blue die, D1, its value is sampled from this distribution die. And similarly, D2 is also independently sampled from this distribution. Another thing you can do inside infer is you can condition distribution. So we can condition on the information that the sum of these two dice is 7. And finally, what infer actually does is it takes an expression and computes a conditional distribution over that expression. So here the expression of interest is, well, is D1 greater than or equal to 3 or not? And what infer will do is give you a distribution over possible values of this expression. Okay, this is a Boolean expression, so the distribution should be over true and false. That's what the support of the set of Booleans is. And indeed, when you run this program, here's what you get. You get 2/3 and 1/3, which is exactly the same answer as we got doing this by hand. That's the first etude. Now, here's the joy of church. The joy of church, the joy of scheme is that you don't just have to do inference over Booleans and numbers. You can do inference over any kind of object in the language, inference over pairs, lists, even programs, because code is data in scheme. So let me show you an example of how that might work. So, okay, your friend Quinn is back. Quinn shows up now with a deck of cards, and she says, look, I really like cards that are blickety. And you say, okay, Quinn, what does blickety mean? And Quinn says, shh, I won't tell you. But she says, okay, I've separated out the blickety cards from this deck, and now I'm going to show you some. And she repeatedly picks up a blickety card and shows it to you, and then puts it back, and then with replacement draws another one and shows it to you, and over again. And here's what you see. You see the king of clubs, the king of clubs, the jack of clubs, the jack of clubs, the jack of clubs, the queen of clubs, the queen of clubs, the king of clubs, the queen of clubs. And then you look at all of these outcomes that have happened over and over again, and you think, well, based on this data, what does it mean for a card to be blickety? Okay, someone in the audience, please, just could you call out a hypothesis, a theory, a definition? What does it mean for a card to be blickety? Great, thank you, person in the audience. Person in the audience says a blickety card is a face card from the club suit. I agree, that seems right. Let's write a probabilistic program that makes this inference. Okay, so how would such a program work? Well, it's doing inference over the space of possible definitions of blickety. And let's say that we're going to model definitions of blickety as little predicates, little scheme predicates over cards. So we're going to start by writing a little generator of predicates. It'll generate predicates like clubs question mark, spades question mark, or more interestingly, not face question mark, or and red question mark, not face question mark. You can see these are all just scheme predicates that can be generated by a probabilistic program. How do you write this program? It's actually not that hard. A predicate of some depth, well, the depth has to be greater than 0, and if it is, then we're going to sample uniformly from production rules and a grammar over possible predicates. So for example, the terminals in this grammar are these atoms like clubs question mark or spades question mark. And the non-terminals are these combinatorial operators, things like negation or conjunction or disjunction. And notice that you then make a recursive call to the predicate generator. Now, I want to be clear about one thing here. This does not define a uniform distribution over all predicates. Why doesn't it do that? Well, think about what it takes for this probabilistic program to generate not face question mark. You have to get lucky twice. The first time you get lucky is you pick not. And then the second time you get lucky is in the recursive call, you have to pick face question mark. Whereas if you were just generating clubs question mark, you only have to get lucky once. Just at the top level, you have to pick clubs question mark. So there's higher weight, there's higher probability of generating clubs question mark. And in fact, you can think of this generator as naturally inducing this prior where simpler predicates have higher probability than more complex ones. Okay, once we have a predicate, we need a way of taking all of the cards that match that predicate and pulling them out of the deck. That's not hard to do. Let's write this little program. Note that because it's scheme, we can use eval to convert code as data into code as code. And so that's how it works. Let's write a function called makepile. It takes as input a predicate. What does it do with the predicate? Well, it evals this little meta probabilistic program. And what that does is sample a card from the deck and condition that it matches the predicate. Great, we're almost done. Let's write the actual inference now. How does that inference work? Well, we start by sampling a predicate, and we turn that predicate into a pile of cards, and then we say, okay, well, for each card that I observed Quinn pull out of that deck, I'm going to condition on the fact that that card was sampled from our pile of cards that are blickety. And finally, we're going to generate a distribution over predicates pi. So okay, again, what this program should do is output a probability distribution over predicates. So it should look something like this, a probability distribution over predicates. And indeed, when you run it, you get the highest weight. The mode of this distribution is and face question mark, clubs question mark, which is exactly what our friend in the audience said. Okay, I think these are all the tools we need to write the program that I really want to write. So let's try to write it. We're going to try to write a program called Gogine. And what does it do? Well, it takes as input a history of past guesses that it has made, which could be empty. And in fact, on the first guess, it has to be empty because it hasn't made any previous guesses. Okay, and then what does it do? Well, it performs inference. And what is this inference over? Well, it's inference over programs. So we're going to sample some hypothesis gamma, which is a hypothesis for who I am, right? Then, just like with the cards, we're going to loop over all of the data we've seen, so loop over each H in our history, and then we're going to condition on having made that guess. So what does that mean? Well, we're going to condition on an equality between what we actually guessed and having sampled from gamma. So a sample drawn from running the probabilistic program gamma, which is our hypothesis about who we ourselves are. Okay, now we get into just a little bit of trouble, because remember, gamma is a program just like us, which means it takes as input a history of past guesses, but now we've lost the pointer to past guesses, right? Gamma needs to be called with input all of the guesses that came before little h. So, okay, this is nothing we can't fix, it's just a little annoying. We're gonna loop not directly over the list of past guesses, but rather over postfixes of that list. So what does that tell us? Well, a postfix of this list is a pair, because lists are pairs, and the head of that pair, or the car of that pair, is a guess, and the tail of that pair, or the cooter of that pair, is the previous guesses, which is exactly what we want. Okay, so again, what do? Come on, buddy, work with me here. What do? We condition on having guessed that guess. To do that, we assert an equality between what? Well, the actual guess, that's head of H, and a sample from gamma, which you can get by evaling gamma, giving as input tail of H, so all of the guesses that came before guess H, and that's it. Then we say, please compute for me a conditional distribution over gamma, over hypotheses for who I am. Okay, by the way, I had in this program, the generator of programs. You might wonder what that's like. It's just like the generator for predicates. So it looks like this. Well, to generate a program of some depth, you condition on that depth being non-negative, and then you uniformly sample from various productions that define a grammar over church programs. So things like sample and condition and so on and so forth. Now, sometimes I say this, and someone objects. They say, okay, Kartik, hang on a second. Shouldn't you also be inferring program alongside Gogine? I think that's a really incisive critique. I think that that's really perceptive, right? Like what is the status of program? Is it part of Gogine or not? Well, I don't know, it's not clear. However, let me say this. If we were to infer program, what grammar would program be drawn from? Would it be a grammar called grammar? And then what grammar would grammar be drawn from? Would there be a grammar called like metagrammar? You see how you end up with this like little problem of infinite regress. I think this problem was most forcefully articulated by Jerry Fodor, who is a philosopher, and he wrote this book called The Language of Thought, where he argued that all human minds have this innate built-in language of thought. And part of his argument, or I think one of the most beautiful parts of his argument, is he says, well, one cannot learn a language unless one already has a language. So I think that the madness must stop somewhere. You have to truncate the recursion somewhere, and here we'll truncate it at program. Okay, that aside, that's the program, that's the Gogine. And I just want to be clear, like, this is a real program. This is not a metaphor for a program as my slides often tend to have. This is a real program that you can download from github.com and run. And I want to show you actually what happens when you run this program. So how do you run this program? Well, remember that you have to give it as input a history of past guesses. But the very first time you run it, you have not made any past guesses, and so the history is empty. So what happens when you call Gogine with capital H being the empty list? Well, it makes the following guess. It makes this guess that I'm going to call H1, which is the simplest possible program. I call this the wild guesser theory of self. Because all this program is saying is I'm drawing samples from the prior. Like that's the kind of mind I am. When asked who I am, I just randomly guess from the prior. And of course this is wrong, right? Like this program is not equal to the program on the previous slide. However, it kind of makes sense that this would be the first guess, because remember what I said about predicate generation. I said that the way we defined it naturally induces this prior over simpler programs being more probable. And this is, in some sense, the simplest program that matches the type of Gogine. And in fact, it is so simple that it gets guessed over and over and over again, in fact, like several times. But then an interesting thing happens. The Gogine looks at the history of its past guesses, and it sees, well, wild guesser, wild guesser, wild guesser, wild guesser, and it thinks, okay, something here is suspicious. There might be a better explanation than that I just always randomly happen to select the wild guesser theory. Perhaps I'm a program that always says the same thing. So I call this the omniscient theory. This says I have some innate built-in knowledge of who I am. I don't know what that is, by the way, but I'm gonna sample some hypothesis gamma and say that every time I'm asked to make a guess, it's going to be equal to gamma. Now this is also obviously wrong. It is not equal to the program we wrote on the previous slide. However, not only is it wrong, it's self-defeating, because as soon as you guess H2, you've broken the property that all of your previous guesses were H1. So you guess H2 once, and then you realize there's no way this is true, and you move on to H3. Okay, H3 is an even better guess. Here, it fixes that bug. It says, no, it is not that each time I previously make a guess, it's equal to my hypothesis gamma. Rather, it's equal to a sample from gamma. This is getting pretty good. I call this the memoryless theory, and the reason I say that is because notice, look very carefully, how does it call gamma? Well, it calls it with an empty list as input. It makes the exact same bug that we were so close to making a couple of slides ago. Essentially, this program is saying, look, each of my previous guesses, it was made as if I had never seen a guess before. And that's wrong. But after observing this a few more times, it figures it out, fixes that bug. It realizes, no, I need to loop over the postfixes, and I need to assert equality between the head and the tail and whatever. And there it is. That is the program that we wrote on the previous slide. Let me show you this in another format. So here I'm showing you this plot. Just look at the one on the left. On the x-axis are guesses, so first guess, second guess, third guess. Or you can think of it as the number of previous guesses you've seen. And on the y-axis, I'm showing you the distribution over guesses that are made. Each of these lines is one of these hypotheses that I talked about. And of course, there's many, many others, because that grammar generates lots of programs, but these are just the notable ones. And you can see, okay, well, it starts off really liking saying that it's a wild guesser. And some other theories actually make a little bit of headway. But eventually, around 10 guesses, there's this, call it a paradigm shift. Something happens, and it discovers, actually, I'm Gogine. So is that success? Well, I think, yes. We wrote a program that I would say endogenously bootstraps some kind of self-knowledge. But this, again, should be disquieting, because I started this talk by giving you all of these counter-arguments as to why you could never write such a program. And I just want to take a second to reflect and think, well, how did we get around these? So, okay, here were the counter-arguments. The first one was the circularity objection. You can't get something from nothing. Except, notice that there is something exogenous here. There's the program, but then there's the interpreter, and there's the random number generator, and there's the hardware that it's all running on. In the same way that there's a mind, but then there's a brain that the mind is running on. There's neurons, there's activations, and that's external to the mind. And I think that's what solves this problem. I think one way to think about this is this little quote from The Catcher in the Rye, where Holden Caulfield says, how do you know what you're going to do till you've done it? actually doing something teaches you something because you don't know what you're going to do until you've done it. So something there must be external. That's my answer to the first objection. The second objection, okay, this was the empirical observation that AI models collapse if trained on their own data. So like what's going on here? Well, notice that a large language model doesn't know that it's being trained on its own data. Whereas the probabilistic program we wrote, it's designed to update its belief in a model-based way. It knows that the data it's being given was guessed by itself. And I think that lets it integrate this evidence in a principled way and actually learn something in a way that an LLM doesn't. Okay, finally, Emerson Pugh, who says if the human brain were so simple that we could understand it, then we would be so simple that we couldn't. How did we get around that one? Well, here I think when we think about representations, they need not be explicit. In fact, some representations can be implicit. For example, the space of all possible hypotheses, all possible programs, is very large, but we represented it implicitly with this small grammar that generated them. And so I think implicit representations, for example, the self-representation being implicit in the conditional distribution over program and the data that it's conditioned on, I think that's how you get around the representational problem. Of course, I think it's the case that even having answered these objections, there was always the possibility that it wouldn't work, right? Like it's possible that the dynamics of the system are such that even though there exists this fixed point where it does repeatedly guess itself, you never reach it because the dynamics are just weird. And so there's something interesting here, something empirically true, something worth explaining. And in fact, I bet you all have thoughts and questions about this. As PL researchers, I can kind of anticipate what you might be thinking right now. And you know, if we were to have a lot of time for questions, I'm sure you could come up with lots and lots of really good ones. Please ask me those in the hallway. The question on my mind right now is different. It's the question, what does this program teach us about what it means to be human? Which is perhaps not a PL question, though arguably it is. I think there is an answer to this, and I'd like to offer you mine. Guys, I think I'm not wrong in saying that the time we live in, the time is out of joint. By which I mean, well, I don't know if it's the decline of democracy. I don't know if it's the rise of AI. I don't know what it is, but I think we live in a time when we as people, as nations, and as a species are being faced with the question again, who are we, what kind of people, what kind of minds? But I think on top of that, there's this kind of nihilism about the question. Is it answerable? Is there an answer at all? I think we might be dangerously close to concluding perhaps not. And if that's the case, well, I don't know. I think things break down. I'm worried about this. And I think the program that we wrote, in its own tiny little way, is a kind of existence proof that it's possible to build a system, creature, mind that does, in its own tiny little way, endogenously bootstrap a kind of self-knowledge that it didn't have before. It's at least possible. And if you're willing to grant that existence proof, then I think you might be willing to say, at least it's possible for us too, we radically complex creatures, humans too might be able to learn something about ourselves by reflecting on our own reflections. And if you admit that, then you might think, well, how do we do it? And I think this teaches us that the way to do it is to look to our past, to look to history. In a time when history feels mutable, for sale, up for grabs to those with the most power and the most influence, I guess the thought I want to leave you with is the importance of looking to the past as a way of learning about us, about the importance of looking not just at the art of the past, but the history of art of the past. Not just science, but the history of science. Not just literature and philosophy, but the history of literature and philosophy. Thank you.
Thank you very much. much, Kartik. Are you open to questions now or in the hallway? You mentioned the hallway.
Either way is fine.
Okay, does anyone have a question? I know it's not necessarily the kind of talk one follows with questions, but we're very open to questions.
I hope this is sufficiently philosophical to be asked now. But I think you touched on this a little bit towards the end, which is that, so your point about generating a program, the sort of grammar of thought for this Gorgon, you said, well, it doesn't make any sense because you described this hierarchy of meta languages that you would then need to, and you say that essentially one of them needs to become this implicit language that is used for generation. I didn't know. It's a little loud. Is it fine now? Okay, it's fine.
How about I return it to you and I'll speak a cappella?
Um, And I didn't fully understand this point because you're in the list and the language is itself. And in some sense, I feel like you could have written a sufficiently complete grammar. Could have, well, obviously very difficult because it's not a difficult complete code that just generates, right? And I mean, philosophically, I think the point is the same. There is somehow some sort of external. Should I use this? Hello? Does this work better? I'll stand back from this microphone. I think it works out to be the same thing, but I'm curious why you think you would need metagrammars. Like, why is there this hierarchy of thought when the context that you're working in is this sort of self-recursive language? Mm. Yeah, I think the point is, I think the thing that I was more imagining, especially from the abstract, was that you might say the hypothesis space is I am a program. And this is the baseline for this program. And then of course, maybe it doesn't converge nearly so neatly. And maybe perhaps it doesn't converge at all. It's so much harder. But maybe, I don't know if that elucidates a bit more, something about, how we develop. In fact, maybe if you find that this other version is just incredibly inefficient, it never gets anywhere, then maybe it does really say something about how much sort of prior structure we already have before we get going, because we have to do all the same inference, and we don't really work from really just a blank slate of being I'm a mind. time to try that. I don't, but thank you. You can hold.
Any more? Yes, please.
So this is, of course, related to the previous question, because I think that is the crux of the issue. So in the card example, if you don't put any model of models into the system, you would expect that the correct answer is that Blinkity means that it's either a heart of, what is it, a queen of spades, a king of spades, or a jack of spades, right? So the fact that you can abstract over suits, you can abstract over being a face card or not, is built in. But if you didn't really have that, right? If you really started from the ground truth, which is that I have this finite set of 52 cards, and anything more than that is here, not in the cards, then you would get this answer. And so my question is, would you find that satisfactory? And of course, I'm not asking about cards, I'm asking about the translation of this question to the mind.
Yeah, so for example, so you're saying, look, the hypothesis space for cards, I said it was these like structured predicates, and I just sort of asserted that there are these predicates like red question mark and face question mark, and there are these like logical combinators like negation and conjunction and disjunction. But where did those come from? And couldn't you do the same thing by having a hypothesis space that is just all 2 to the 52 subsets of possible cards? Okay, so first of all, I think if you did it that way, if you had that hypothesis space of all 2 to the 52 possible subsets, and if you put a uniform prior over them, it would still work. It's not intuitively obvious that it would still work, but I think there's reason to believe it would still work, which is to say that if you showed enough data, it would converge to the correct subset. And I'll let you puzzle out why I believe in that even strongly. But okay, so the question really is like, why not do that? Well, I think in some ways the model that I showed you is kind of a hypothesis about what our built-in concepts are when we think about sets of cards. So for example, you could imagine introducing a new concept like prime numbered cards that are red, and you could imagine running the same inferences, and if you will, does this make the same predictions repeatedly? So if I were to show some data, like suppose I showed you like the 3 of hearts and the 5 of hearts and the 7 of hearts, and you just go around and ask a bunch of people like, okay, given this information, is 9 of hearts also part of this set? Well, it's an empirical question, right? Some people might say, yeah, it's odd numbered cards that are hearts, and other people might say, no, it's prime numbered cards, and you'd have to go out and ask a lot of people to get some data on what people's intuitions are, and that will help you reverse engineer whether or not this primitive is going to fit people's intuition.
But could you do that internally to the system by basically saying, okay, I have not only all possible subsets, but also like this infinite space of all possible predicates, and because your distribution kind of in some, hand-wavy sense corresponds to the Kolmogorov complexity of the predicate that you're going to get, you could hope that maybe then you can synthesize a tight predicate which is neater than just listing out, like selecting the subset as a subset literal, basically.
Yeah, I think you're, I think, I don't know, I think these really are kind of very deep mysteries about how we think, like where do these concepts come from? In the case of cards, of course, like they're just given to us, right? Like cards just have this like structure to them and we talk about them all the time. But in general, where the concepts that we apply to the world come from, concepts like oddness and evenness, which had to be invented in some sense. Why do some concepts endure and others not? Like, these are questions our lab thinks about all the time, and I have opinions about it, but I think it's actually up for debate, and yeah, we should talk more over lunch, I think.
Thanks.
But I think those are some really good questions.
I have a really simple question, which is, did writing a successful Gauguin give you any insight into yourself personally?
Right. So every time I gave a practice version of this talk, someone inevitably said, Kritik, what if you did another meta level and thought about how... so I was debating this. Look, I mean, I don't know, right? Like, undoubtedly the thought of writing this paper taught me something about the kind of person I am. Like, it must have, because it's more information about me. But what is the content of that knowledge? Well,
short question. Is postfixes in the grammar?
Yeah, postfixes I think is a scheme term. I never saw postfixes in the grammar. It might, yeah, I don't know.
Great.
Do we have any final questions? We do not. Okay, let's thank Kartik very much once again. And that is unfortunately the end of this year's Onward. It is